we're going to be continuing our discussion of induction of EMF. And we wish you guys well who are taking the AP Reading Series. So, we're going to begin with homework questions if anybody has them. Actually, while you're thinking about which questions you'd like to ask, I'd like to review a little bit from yesterday, because the important point may have been obscured in some of our details. And the important point from yesterday is Faraday's law of induction. And that is that the EMF, which is just a voltage difference that is generated in a wire, is going to be equal to, but opposite to, the rate at which the magnetic flux is changing on the interior of that wire. And the classic example that we gave yesterday was of a wire loop with some kind of magnetic field coming through it. Here it is. And we're going to switch off that field. And when we switch off that field, during the time that the field is decaying to zero, we will end up generating an EMF in the wire. And if we use our right-hand rule combined with Lenz's law, we can determine the direction of that EMF. So at this point, those magnets are becoming a significant distraction.
All right.
I believe the phrase is, I'm very sorry.
I'm very sorry to speak ignorant.
Thank you. All right. So, what we have is, if this field is decaying to zero, then the wire is going to behave as if it is trying. Remember the anthropomorphism idea. We're going to act as if it has a will here, even though it doesn't. It's going to behave as if it's trying to keep that field coming out of the board. And so in order to do so, it needs to push current in this direction, which means this is going to be plus and this is going to be minus if the field is switched off. And so that was pretty much as far as we got yesterday. Last night you did some homework problems, and so the question is, do you have any questions about them? Good? Will? Do you have a question? No. Okay. Very good. I'd like to extend this idea a little bit by examining this kind of a scenario a little more closely to see exactly what we're talking about when we say that the EMF is equal to the opposite of the rate of change of the flux. So I want to consider a wire loop again. And just for the fun of it, we're going to give it an area of like 1 square meter. Okay? And what we're going to do is to turn on a magnetic field and magnetic field is, what's that? Yep. In fact, Faraday's law is going to be the operating topic all day today. We're going to turn on the magnetic field so that it goes from 0 to, give you a number of Teslas. Make it small. Sure. 1. 0 to 1 Tesla. And so we're going to first turn on the magnetic field so it goes from 0 to 1 Tesla in 0.05 seconds. Then we're going to leave that magnetic field going for a second. And then, after we've left it on for 1 second, we're going to switch it off but it is going to decay slower than it came on because electronics will often have a capacitor or something like that. And so it's going to turn off in 0.25 seconds. In other words, we switch it on, leave it on, we turn it off, and it ramps down like that. And what we'd like to do then is to, first of all, sketch ourselves a graph of the field so that we can see what's happening here. And then I want to compare that to a graph of the EMF that is produced by that field. So our goal here is we're going to sketch a graph of field versus time. And that's easy enough because we know all the numbers. I'd like for you guys to sketch at this time the graph of the field versus the time. Jesse, how did your graph look? I'm confused. Yeah, we are.
Oh, yeah.
Yep. Right, so if you are playing along at home, please draw a graph also. Pay attention and think about at what times. This is how long the processes last. That doesn't tell you at what time. So talk to me, Jesse.
More 0.05
Okay?
and then 1.
Okay. Now we left it on for 1 second, so 1 is not the right time to mark. Should be 1.05. Right. Don't confuse duration, delta t, with the actual absolute time.
Wait, is it 1.095? Oh wait, 1.95 or what?
1.95?
Because the first one says 0.05.
So first, if we start at 0, right? Now picture the camera running here. So then we turn on the magnetic field. That process is complete in 0.05 seconds. So now our time is 0.05. Then we leave the field on for 1 second. So our time is now 1.05.
Oh yeah.
Yeah. And then we turn it off.
And 1.25 starts 1.3.
Yep, there you go. Okay, now what does my field look like?
Going up to
Yep.
0.05 and then stays within until 1.05.
Yep,
And then, goes down until 1.3.
there we go. And we got 1 Tesla right here, marked like so. And let's be good about our graph and put seconds on the time, and Teslas on the field, and all that. You look a little puzzled about something.
I don't understand the.
Well, I gave you durations for each of these events, right? And so if we start at 0,
Oh,
and we march along, and add these
I
durations.
didn't have this here.
Oh, gotcha. Gotcha. Yep. Okay. Now that we have this guy right here, here's what we want to observe about it. During the time in blue, the very short time while the field is turning on, the rate of change, that's what I wanted to say, the rate of change of the field is positive. And because the rate of change of the field is positive, the rate of change of magnetic flux in that wire will be positive also. Because flux is equal to, what is it? Yep. E cosine theta, exactly right. So if I increase my field, I'm going to increase my flux proportionally.
Why is the units Weber?
Ah, that's a great question. Yep. So that's just a unit that we use to capture Tesla meters squared. So 1 Weber is equal to the same as 1 Tesla meter squared, and you noticed that in your homework last night. Yep. So we could, so if we were to do a graph of the flux would have the same shape. Okay. Now, here's the deal. Because the EMF is equal to the opposite of the rate of change in flux, and that's Faraday's law of induction, then to find the amount of EMF during this time, we are going to take the slope, the rate of change of each of these pieces of graph, and then take their opposite as the EMF. So that while the magnetic field is increasing, my EMF is going to be negative. And while the magnetic field is flat, constant, my EMF is going to be 0. Yeah, there is 0 slope for that. And while the magnetic field is decreasing, my EMF is going to be constant. Exactly. And in fact, because these are straight lines, it's going to be a positive constant. What positive constant? Well, let's find some slopes. What is the slope of the blue line? Process number 1. Exactly. It's 1 Tesla over 0.05 seconds, which is going to be 20 volts. Tesla meters squared, excuse me, which is going to be 20 volts. So that during that 0.05 time period, my EMF generated is going to be the opposite of the change in flux, which is going to be negative 20 volts. Then, during process 2, while the magnetic field is left on, and we do it in red so that it corresponds here, we're going to have a slope of 0. So that my EMF during that time period from 0.05 to 1.05 is going to be 0. Yes?
Why is the 20 in a straight line?
Down here.
Yeah.
And I really probably shouldn't have connected it like that. We should just make it a step function. Okay? So, from Faraday's law, the EMF generated is the opposite of the slope. Take a look at this graph right here. You can see we have constant slope because we have a straight line in the blue portion, and therefore we're going to have a constant EMF down here. And now during the green portion, my rate of change of the flux is going to be equal to negative 1 Tesla, because I'm losing field, final minus initial, over 0.25 seconds. Tesla meters squared, I should say, over 0.25 seconds, which gives me negative 4 volts. And the EMF generated is the opposite of that, so then I'm going to get positive 4 volts all the way from 1.05 to 1.30 seconds. Now, if you're in calculus, you can look at this and see, oh, what we just did was a graph of F prime from a graph of F, except that it's upside down. These jumps right here are graphed as if they are instantaneous. In real life, they will not be purely instantaneous. They'll be sort of connected and rounded. And these little corners right here will actually be slightly rounded also. That's real life for you. But as a simple model, we're going to consider that as a piecewise function. How are we doing? Tomorrow I'm actually going to demonstrate this. In fact, Josh, would you bring the magnets back tomorrow?
Sure.
That way we can play around with them.
I'll have to like keep them here because I have the calculus.
Oh, right, okay. That's fine. I've got it. So I'll just see. Okay, now I'm going to come back and visualize that physically. Here we visualize the graph. Our EMF went from negative to 0 to positive. I want to come back and visualize what's happening physically here using Lenz's law in our right hand. Okay? So, at first, we turn on the magnetic field. And as we turn on the magnetic field, it goes from 0 and then it starts to charge up. And let's just say that it's coming out of the board as it makes it like easiest. Okay? We like to use Lenz's law and our right-hand rule to determine how the EMF is going to go. And the way that we're going to do that is that we are going to consider the change in the flux that is taking place, and we're going to try to oppose it. And the opposition is that negative sign in Faraday's law of induction. Okay? So the change that is taking place is we're going from no flux to flux from a field coming out of the board, right? First, identify the initial situation, no flux. Then identify the final situation, which is field coming out of the board. And now we're going to try to get the wire to react to oppose that change. In other words, it's going to attempt to bring the flux back to the initial state. And the initial state was 0. Well, so the reasoning now is, if I have field coming out of the board, and I need for the total field to be 0, then the wire has to generate field in which direction? Parallel or which? Well, okay. Which direction then? The field is going this way, right? So if we want to oppose field going this way, we have to generate field going into the board. Exactly. So our initial state was B equals 0. The final state is B out of board. And so reasoning with Lenz's law, I'm going to try, the wire is going to create field that will try to cancel the field out of the board and bring it back to the initial state. It will not be successful, but during the change it will attempt to do that. So therefore, we conclude that the wire is going to generate field into the board, and now we use our right hand to figure out which way the current is going to go based on that. And to go into the board, right hand, we have to have current going this way, and as a result, that gives us our direction for our voltage. We have to have a positive here, a negative here, to force the current to go down. So this is actually a somewhat sophisticated piece of reasoning. Once you get used to it, it goes quickly. So let's kind of take it in slow motion so we can see what's happening. We identify our initial state, which is 0. We identify the final state, which is field coming out of the board, and we say to ourselves, what do I have to do to get back to the initial state? I have to cancel the field coming out of the board with field going into the board. So then we use our right hand to figure out how the current should go to make that happen. Current should go this way. And notice that it's never the case that you would be confused about that, because no matter where you grab the wire, if you want current to go into the board on the inside, your thumb has to be pointing in this direction. So it will always work, no matter where you are on the wire. And so based on the direction of current, we then identify plus and minus, because current always flows from positive to negative. Question, Dan? Good? All right. So that was our turn on. Now let's look at the turn off state and use the same reasoning. In the turn off state, we are going from an initial state of field coming out of the board all right, and we are going to a final state of 0. Well, if we're going to oppose that change to try to get the final state back to the initial state, then which way does magnetic field have to go? It's got to go out of the board, and so using your right hand, how can I get magnetic field to go out of the board? Yep, current has to flow in this direction, and if current is going to flow in this direction, boom, boom, there's our plus, there's our minus. And if we compare, this was process 3 here while the field was turning off. If we compare that to process 1 while the field was turning on, we can see that our pluses and minuses have been reversed here physically. So our right hand tells us exactly the same thing that our EMF graph holds. And that is that during the turn-on process, we're going to have plus and minus in one configuration, and in the turn-on process, and in the turn-off process, the plus and minus will be reversed. Okay? For the remainder of our time, what I'd like to do is to take a look actually at some of the homework problems for tonight, and walk through using Lenz's law to predict direction of current flow. So let's take a look at number 4. Excuse me, number 9. And in number 9, what we have are 4 different configurations where we have a wire, like so, that is carrying a current, and we have a wire loop, like so, that is going to have magnetic field going through it as a result of the current that is flowing. And in question A, they have current flowing in this direction, and they tell us that the current is increasing. And based on this, they'd like for us to draw the current that is going to be induced in our wire loop as a result of the changing current right here. Now the first question is, why should there be any current induced at all? And the answer has to be because there is a changing magnetic flux. Well, where's the magnetic flux coming from? Oh, wait a second. Magnetic field is created by moving charges. That's right. And the moving charges are happening in this wire right here. So the first thing that we're going to need to identify is which direction is that field going? For that we need our right hand. Here it is. All right. So tell me how to draw the field around the straight wire here at the top. Use your right hand. And so what does our right hand tell us? Field is going to go in which direction? It's going to go out on the bottom and in on the top. Right. So we can draw ourselves a couple little X's like so, and then we can draw the field coming out on the bottom. Okay. So that's our right hand. Now, if all that was happening was the current was flowing, and we didn't have increasing current right here, but it blocked this off, then we would have a constant magnetic flux in this wire, and there would be 0 EMF induced. But that's not what's happening. What's happening instead is that not only do we have current, but it is increasing. High. Oh my goodness. We've never had a hand-delivered virus message in this classroom before. This is a new era. Okay. So not only do we have magnetic field here, but the magnetic field is increasing. Okay. So, with the idea of identifying initial and final states, let's mark it like this. And usually, honestly, I do this initial and final state thing mentally, but as we're getting started with it, we can explicitly write it out if it'll help keep your head straight. So in my initial state, I'm going to have some magnetic flux from the field coming out of the board, right? In my final state, I'm going to have even more magnetic flux from a stronger field that is coming out of the board. So let's say it like this. In my initial state, I'm going to have a positive flux, and in the final state, my flux is going to be greater. In other words, the flux is increasing. Okay, simple question. My wire is going to react so as to oppose the change. In other words, it's going to try to reduce the total amount of flux in here. If it's going to do that, which way does it have to create a magnetic field? Into the board. That's exactly right. And so our thought process is if the wire creates field into the board, and if it's going to create field into the board on the inside, always the wire reacts to what's going on its inside. Field into the board on the inside, and that means current is going to have to flow in this direction right here. We can check that with our right hand and see that the wire is going to induce some magnetic fields here that will cancel out the increase in the flux. Yes, ma'am.
Do I understand why did you do the
Why did I do it? I wrote it down explicitly so that I could think clearly about what change is taking place so that I could get my wire to oppose that change. So we're looking at how things change in order to determine the induced EMF.
So, what does it mean for that the IV is greater?
The flux actually is feeding.
Yeah. How does that affect the field?
Oh, okay. Yeah. So let's look at it from the perspective of Faraday's law and the perspective of Lenz's law. We're really using Lenz's law here without actually computing, but we could have done it using Faraday's law. From the perspective of Faraday's law, the EMF generated is going to be the opposite of the rate of change of flux. And so, since my rate of change of flux is positive because my field is increasing, because the current is increasing through this wire, so that's a lot of cause and effect chains here. Since my flux is increasing, that means that we're going to generate a negative EMF. What does negative mean in this context? Negative means in this context that it's going to generate a magnetic field in the opposite direction of the field that we have there. Now, from the perspective of Lenz's law, which is that the field created, that the wire will create field that opposes the change in flux. The wire will create field that opposes the change in flux. Our change in flux essentially is positive, because we're going from lower positive flux to higher positive flux. So my wire will create field that essentially creates negative flux. And that means that the field is in the opposite direction of the area vector, and there you go. Does that help? So once you get used to just assessing very quickly the initial and final, you can do an opposite change really fast. And with practice, Lenz's law can be done in a couple of seconds. Don't worry if you're not there yet. Let's take a look at one more in that problem, C. And in C, we have a wire loop again, and we have a wire on the outside, and we have current flowing this way, and we are told that the current is decreasing. So now, based upon that, I'd like for you guys to figure out which way current will flow in the wire loop here. If you want to skip ahead to the answer, then you should have gotten this. Yes.
And how do you tell when the flux is positive or negative?
Good question. Okay. So we're going to start with our current right here that generates the magnetic field. And because of the current, we're going to get a field that is into the board on this side. Plus and minus is kind of arbitrary, but if we take the area vector to be pointing outside, what we have is negative flux. Okay? And that negative flux is decreasing. It's becoming less negative. So our initial state is so watch this carefully. A decreasing current leads to an increasing amount of flux only in the sense that it's becoming less negative. So if I look at the flux right here versus time, my flux is starting off negative and it's becoming less negative over time because my current is decreasing. So that I want to generate additional magnetic field into the board to counteract that change, which means my current has to be going counterclockwise. Clockwise. Yep. Right direction, wrong. Adverb. Sure, absolutely. In fact, Josh, would you be willing to go ahead and do B and just talk your way through B?
Okay.
We have, again, our wire loop. And again, our current, which is going in this direction. And our current, in this case, is decreasing. What do you like to go by?
I'm not a teacher, so I first use my right hand rule, so it's wait. Yeah, it's going out more on this side into more on this side. Okay. So
Yep.
the inside here is going to resist, meaning it's opposite. So at the start,
Okay, good. So we have a slight misconception. The inside is going to resist change, not necessarily the field itself. So that's an interesting distinction. Notice that I cannot go from field is out of the board here to field must be into the board for the loop.
okay.
So the only thing, everything else you've done is great. Notice that he focused on the interior right here, which is exactly where we want to look. This is the field that matters, okay? But we're going to have to look at how that field changes in order to determine how this wire loop reacts.
Okay.
Does that make sense?
So, okay, I0 starts off,
It's phi, not I.
right, phi starts off like that, and then it decreases over time.
Okay, how do you get negative?
It gives me that the current is decreasing, so therefore the change has to be decreasing.
The flux itself is going to be determined, the sign of that flux is going to be determined by the direction of the field and the direction of the area. And in this case, the field is coming out of the board. Area vector we're going to take to come out of the board. All right? So that means that because the two of them are in the same direction, theta is 0, cosine theta is 1. So actually our flux is positive. So the sign, notice that this was the inverse of the problem that you had earlier. The flux itself is a quantity that is instantaneous at any given moment. The rate of change of flux has been the derivative of that.
Okay.
So our flux is positive,
Right, but then it's decreasing.
then it's decreasing, that's right.
So, okay. So,
Does everybody see how the analysis goes so far? Have you gotten the same results? Okay.
all right. So, I don't know what to do in this case.
Aha! Now we appeal to Lenz's law. The wire will generate a current that will oppose that change.
Okay, so it'll try to keep the flux up.
Yes.
Okay.
field in which direction?
Let me write it out. So it's going to try to keep B the same.
Yes.
Okay, so then B will remain the same.
Yeah. The
if
wire
the
pushes
current
field which way?
goes that way.
Okay, and let's check with our right-hand rule. If our current goes this way, that's going to push field
Oh
into-
yeah, I'm going the wrong.
Oh, wrong way, okay. So then that way.
Yeah.
Yep. Then that will push field out of this loop on the inside, which is what you want. That's it. You got it. Good. Good. It seems like we want a little more practice with this. We've got a few minutes, so let's actually do some more like this. Let's change our configuration a little bit. Let's give ourselves a square wire loop here. And let's have a magnetic field that is going to be created by a big magnet. So let's have it come forward. And decrease it. So go ahead and draw that state on the board, and then decrease it, and then tell me which direction we are going to experience current. Yes. In this particular scenario, I'm envisioning that field is coming out of the board everywhere. The older I get, the faster I want to draw field.
So 2 seconds from now, you'll do it faster.
Mm-hmm. Now, Josh stumbled on a way to shorten our thinking a little bit about Lenz's law here. Notice that D is out of the board and B decreases. We can oppose the change in flux if we just oppose the change in B, right? So if the change in B is to decrease, then the opposite of that is B increases. Exactly in which direction? Out of the board. That's right. So B has to increase out of the board. To make that happen, boom, right-hand rule, and now we know which way the current goes. Already, Lenz's law is seeming a lot easier, right? Just have you done to it. Yep. Our change in field was to go from out of the board to decreasing out of the board. If we want to oppose that change, then we have to increase our field out of the board. And to do that, right hand, and there it is. So this was good. I'll see you tomorrow, and we will extend this a little bit.